of our definition of a limit. So using limit notation, you can write, so the limit of f of x as x approaches 1 is equal to 3. So make sure that you're aware of how to read this. It's going to be very important that we communicate effectively in this class. So you need to know that when you see something like this, it says the limit of our function f of x as x approaches 1 is equal to 3. This discussion leads to an informal definition of a limit. If our function f of x becomes arbitrarily close to a single number, L, as x approaches c from either side, the limit of f of x as x approaches c is L. So this is how that whole little wordy thing is represented. So it says the limit of f of x as x approaches c is equal to L. So if we can prove that as x goes to a specific value of c, that on both sides of c it approaches the same value of L, then therefore it is the limit. So let's look at a little example here. It says estimating the limit numerically. So here's our function. F of x is equal to x divided by the square root of x plus 1 and then minus 1 at several points near x equal to 0. Use the results to estimate the limit. So we want to find our limit of our function as x approaches 0. So what we would do is we would look and say, okay, well, we want to know when x is equal to 0. And if we could, of course, we would love to just plug 0 in. But that's not going to help us out. It's going to give us 0 divided by, that's going to be 1 minus 1, which is 0. So that wouldn't actually allow us to calculate the value. But as you can see, using our estimating, as we get closer and closer to 0 from the left side, so this is where our notation comes in, the limit of our function as x approaches 0, to show from the left side, we're going to say the numbers that are less than 0 and use that negative exponent. You can see as the values get closer and closer to 0, they're going to get closer and closer to obviously 2. And then we can show on the right side the limit of our function as x approaches 0 from the positive little exponent there, or the numbers that are greater than 0, or the right side. As we get closer and closer and creep our way back towards 0, what happens is the numbers are going to decrease and get closer and closer to 2. So therefore, we can say that the limit of our function as x approaches 0 is equal to 2. Let's go on to the next slide here. And this is a little graphically, it shows you a little bit of example. From the results shown in the table, you can estimate the limit to be 2. The limit is reinforced by the graph of f of x. And again, you can notice there's a hole there. If you were to graph it on graphing calculator, you would not see that hole. But the function's undefined at 0. But the limit of f of x as x approaches 0 is 2. Which we found numerically on the last slide. So in example 1, note that the function is undefined at x equal to 0, and yet f of x appears to be approaching a limit as x approaches 0. This often happens, and it's important to realize that the existence or non-existence of f of x at x equal to c has no bearing on the existence of a limit. So just like we talked about, even though the function is not defined at this point right here, because both sides are approaching the same number, the limit still exists. So a very important concept that we're going to be using often whenever you're asked a limit question.